Welcome back, physics fans, and we're ready to go on the second lesson for static equilibrium. The first lesson was on translational equilibrium, where the sum of the forces have to equal zero. So we have the sum of the forces have to equal zero in the x and in the y. We learned about torques overnight and just went through that. So that is rotational equilibrium. And now we're going to talk about static equilibrium, which has to do with all three of these conditions. The first condition of static equilibrium and the second condition of static equilibrium. Translational and rotational equilibrium. Okay, so let's just quickly go over the torque part again. So torque is a leverage, the rotational equivalent of force. If a net force or net torque acts on an object, the object will spin. Although the torque is a vector, we write it as a scalar equation in physics 12. Okay, so torque is the force times the distance times the sine of the angle between that force and the distance. And we're going to treat it as a scalar, but it is actually a vector, but we're in physics 12, we'll just leave it as a scalar. Okay, that's just our formula for it. If a force acts at the pivot point, then the torque is, so if we have an object and the fulcrum is right there, the pivot point is right there, and we apply a force at that point, the torque caused by that force is zero. Why? Because d is equal to zero. The distance to the pivot point is zero. If there are several torques acting on the object, then the net torque is the sum of the torques. Torques are just additive. On an object, if the net torque is counterclockwise, then the object spins counterclockwise. If on an object the net torque is clockwise, then the object spins clockwise. If the object is not spinning, then the sum of the torques equals zero. There is no net torque. Net torque equals zero. If we adjust the angle at which the angle in the torque formula, which angles give the maximum torque? And we want R, or so what's in D in the formula, sorry. So D has to be perpendicular to the force. And in this case, that makes the sine of 90 to be maximum. We want it to be 90 degrees. And the minimum, we want D to be parallel with the force. That we really want the angle to be 0 degrees. Or 180, as long as it's parallel. And this is one of the things here that I talked about yesterday, that supplementary angles have the same sine function. Therefore, it doesn't matter if I take theta over here or theta over here. Yes, they are different angles, but the sine of those angles are going to be the same. So the torques, it doesn't matter which angle we use. Okay, so let's do static equilibrium right now on a balance beam with one object on it. Okay, the 5 meter long beam and the mass hanging from it are in, boom, rotational equilibrium. So what is the net torque on the beam? The net torque on the beam is 0. Why? It's in rotational equilibrium. That's the definition of it. Okay, let's change this to a green color that we can see a little bit better. So B, find the torque caused by the mass about the pivot point. So this is the pivot point. So here's the answer for that. The torque of this very long beam, which is 5 meters, it's in balance because there's a 20 Newton weight over here, 1 meter away from the pivot point. So what is the torque caused by the mass? The torque caused by the mass, T mass, tau mass, is equal to the force of gravity times the distance times the sine of the angle. That's the torque formula. And in this case, it is 90 degrees, so that goes to 1. And its weight is 20 newtons. And how far away it is from the pivot point is 1 meter. So the torque is 20 Newton meters counterclockwise. That's the torque caused by that 20 Newton mass. Okay, stop me if you don't understand something. Let's do C. Because A and B, because the net torque is 0 and the torque caused by the mass is 20 newtons, because of those two things, then what must be the torque caused by the 5 meter long uniform beam? It has to be the torque of the beam has to be 20 Newton meters clockwise because they add up. So let's draw a free body diagram. Okay, so I'll go to black here. There's the beam. We have 3 forces acting on it. We have the force of gravity, or force of the mass. We have right in the middle of the beam the force center of gravity, and then the pivot point is also pushing up. So the pivot point, it's resting on the pivot point, so that's the force of the pivot point. How did I do that? So there's my free body diagram. So that's going to be one of your first free body diagrams that wasn't a point object, but a rigid object, so it had size. All the forces are acting at different points, so it's definitely a non-concurrent system. And that force of center of gravity is the weight of the beam, but it's acting in the center, so I just call it Fcog. How far is the center of mass of the 5-meter long beam to the pivot point? Okay, so this is E. It says it's a 5-meter long beam. So the center of the beam is 2.5 meters from edge. The center of it is halfway through it. It has to be right in the middle. And so how far is it from the pivot point? So the, it's like right there in the middle of the beam. And this whole distance here is 2.5, but that is 1. So it's going to be 2.5 minus the 1. So that's going to be 1.5 meters. That's the answer to E, 1.5 meters. How far is the pivot point to the center of mass, or how far is the mass to the pivot point? And now we'll do F. We'll write down the torque formula for the mass of the beam. So torque formula for the beam. Torque formula for the beam is force times distance times the sine of the angle. That's the torque formula. And we're told that the torque of the beam, or we calculated it in C, is 20 Newton meters. The force of gravity of the beam is just mg. The distance is 1.5 meters, and it is the sine of 90 degrees, which is 1. Because it's straight down, it's perpendicular to the beam. So here we get m is going to equal 1.36 kilograms. Let's just show it to you. We get 20 divided by 9.8, the g, and also divided by 1.5, 1.36 kilograms. So that's how heavy the beam is. So one more thing we need to do, and that is G, what is the force pushing up with? If you take a look at it, we were given that this is 20 newtons, the mass. We just calculated that this is 13.3 newtons. Maybe we didn't calculate that. This times 9.8 is 13.3. Force of gravity is mg, and that is 1.36 times 9.8, and that's going to be equal to 13.33 newtons. So if the mass is pulling down with 20 and the beam is pulling down with 13.3, to keep it in translational equilibrium, then the pivot point has to be pushing up with 33. So the sum of the forces in the y direction have to equal 0. That means the forces up equals the forces down, and the forces down are equal the force of gravity of the mass plus the force of gravity of the beam, and that is 20 plus 13.3, and the force up is the force of the pivot. So the force of the pivot has to equal 33.3 newtons. And that will be up, just in case you wanted to know. Any questions? Okay, let's tackle a couple little concepts before we do the next example. Well, that's actually, sorry, the concept is the next example, but translational equilibrium, an object whose center of mass is not accelerating because the forces are balanced. Rotational equilibrium, it's not spinning because the torques are balanced. In the example number 2, the diagrams below show beams in the top view in space, no gravity. Specify the type of equilibrium that each is in. Translational, rotational, both, or neither. For torques, please take the pivot point to be the center of mass. So we'll put it right in the middle. If you push down here with 5 and push up there with 5, the net force up and down is 0. So it is in translational. It's not going to accelerate through space moving, but definitely this 5 causes to rotate that way, and this 5 causes it to rotate that way. It's not in rotational. It is not in rotational. B. And this looks like the opposite. This is turning down, this is going down, so translational is not. But rotational, if the pivot point is here, it's not going to torque. Meaning this wants to rotate it this way, this wants to rotate it that way, that's going to balance out. So rotational is true. And translational for that one. C. The force is up and the force is down. Balance. So translational, it is. Is it rotational? This one's acting at the pivot point, so this is not going to cause a torque. So this one is going to cause a torque. So rotational, it is not. But D, here we go. This is pulling down with 5, that's 5 down, and that's up with 10. So translational is true. And torque-wise, this one's not going to cause a torque because it's at the pivot point, and that's causing it that way, that's causing it that way, so that's both rotational and translational. Any questions? Okay, and then now until now, all the torques we've been doing, it's been quite easy. All two of them or three of them that we looked at is pretty easy to see where the pivot point is. But what about objects that are just at rest and don't have an obvious pivot point? Consider a person doing push-ups or planking. Where are the possible locations for the pivot point? Around the feet or around the hands? Around the object, the guy's or the gal's center of mass? Or somewhere else? Which should we use? Well, in fact, they all can be used. As long as the object is not moving, any point can be used as the pivot point. The formulas will hold true as long as the object is in static equilibrium. And it doesn't matter where you put the pivot point. The pivot point you choose and then measure your rotational around that. Okay, I'm going to give up on example number 4 right now. Let's do number 5 for me, please. Let's do this. This is going to be a very good one. We have a 45 kilogram person walking out at the end of the diving board. The diving board is 3.75 meters long and has a mass of 10 kilograms. And this guy has 45 kilograms. There are two supports, number 1 and number 2. Draw the free body diagram of the diving board and all the forces acting on it. So I've already started it, and I gave you a box for it, and labeled the center of it, this force called a center of gravity force. So let's draw the force that the man is pushing down on the board with. And I'll call that the force of gravity of the man. Number 2, definitely, I wouldn't want to sit there. I wouldn't want to put my arm underneath there because that board is going to be crushing it. 2 is going to be pushing up. A lot of people will look at this and think that 1 is pushing up as well, but it isn't. Okay? Just imagine if 1 broke, if this broke here. If the person standing on the diving board, this would flip up. It would pivot around this point. The pivot point would be here. And if that's not attached, this guy's going down. It's just a balance beam on that post. And you have 2 forces pulling down here and nothing here. So, in fact, this has to be attached to number 1 and right down to the ground because the force of that one is down. So we do have the force of gravity of the beam. We do have the force of gravity of the man. We don't have force of number 1 and we don't have force of number 2. So here's a big idea. The big idea of this question and many of them. We have 2 unknowns, F1 and F2. But in the torque formula, we will still have two unknowns because there's two unknown torques, because there's two unknown forces. Unless we choose the pivot point at one of these unknown forces, then it removes that torque, then we'll only have one torque. There's going to be four torques here, but if I put a pivot point where a force is, then that torque becomes zero. Then we'll only have one unknown torque. So the big idea here is put the pivot point at one of your unknown forces. So the first time that we're going to do this right now, is we're going to put the pivot point at number 1. What does that mean? If you had to draw it, boom. Let's put this here. I'm putting the pivot point there. Now I'm going to calculate the torques around that pivot point. Okay? So the torques have to equal 0 because he's not rotating and falling off the board. That means the torques counterclockwise have to equal the torques clockwise. Okay, remember the beam was like this, and we had force, 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 and now there's a pivot point there. That is the only one causing it to go counterclockwise. So that's the torque of force number 2 has to equal the torque caused by the center of gravity plus the torque of the man. The torque of the man is down, and the torque of the center of gravity is down, and the torque of F2 is up, if you want to look at it that way. Okay, now let's just expand these torques into the torque formulas. That's the force of number 2 times the distance to the pivot point times the sine of the angle equals the force of the center of gravity times the distance times the sine of the angle plus the force of gravity of the man times the distance times the sine of the angle. Because that's the torque formula, force, distance, sine, theta. Okay. All these angles, if you take a look, are at 90 degrees. Oh, don't do that in your free body diagram. 90 degrees, 90 degrees to the beam. So all these are just 1. The distance of F2 to the pivot point is 1 meter. So F2 times 1 meter is equal to the force of gravity of the center of gravity. The board is 10 kilograms times 9.8. Don't forget the 9.8. And the distance, it's halfway along through the board. So the board is 3.75, and I'll put it over 2. If I already know that number, 1.875, you could write that down. Plus the force of gravity of the man. The man is 45 kilograms. his weight multiplied by 9.8. How far away is he? He's 3.75 meters away from the pivot point. Okay, you do the math on there. 98 times 3.75 divided by 2, and you get 183.75 Newton meters plus, and the guy at the end is causing it 1,653.75 Newton meters. So when you add those up, you get 1,837.5 newtons. And that is what F2 is equal to, because I have to divide it by the 1. So we've been able to calculate through static equilibrium how hard that beam has to push up with to keep it in static equilibrium. Okay, we'll do it again, but now we're putting the pivot point at point number 2. So we have I'll do a sketch of the drawing of the diving board here. We have F2 up, force the center of gravity, and the force of the man, force of gravity of the man. And we have F1 down. Oh, I'll have to mute that off the video. Excuse me. So I'm now going to put the pivot point at number 2. I'm going to put the pivot point right there. So this distance here is 1 meter. This distance, the whole distance here is 1.875 meters. So the distance here is going to be equal to 0.875. I think it's that. Am I wrong? It's 3.75 divided by 2. And then I have to subtract 1 from it. Okay, so that's the distance from the center of gravity to the pivot point. And the guy at the end, his distance is only not 3.75, but 2.75. Just getting some distances there to get ready to throw them into our formulas here. So the torque counterclockwise is the torque caused by F1. The torque caused by clockwise is the torque of the cog, center of gravity, plus the torque of the man. I'm not going to even put the signs in here this time because I already know they're all 1 or 90 degrees. So this is F1 times the distance is equal to the weight of the weight times the distance time, and then this is going to be the weight times the distance. So this is F1 times 1 meter is equal to, I guess it's 10 kilograms. times 9.8 times a distance of 0.875, 0.875. I'll change color here for the next object, the man, plus the man, his weight is 45 times 9.8, and he is only 2.75 meters away from the pivot point. You have to go from the pivot point. These numbers are 85.75 plus the torque caused by the man is 1012.75. So the total torque is 1298.5 Newton meters. So the force of number one is only 1298.5 newtons. So I have the two answers now. What are the two forces? We have the two unknowns, right? We had two forces down there, the board's weight and the man's weight, but we didn't have the two forces. And this force will be up, and this force will be down. Now, thirdly, yeah, you wouldn't have to do a thirdly normally, but I want to show you, and this is our check. We're going to do translational equilibrium. All the forces are up and down. So the sum of the forces up and down have to equal 0. The forces up have to equal the forces down. The forces up is just F2, and the forces down is F1 plus F cog plus F man. There's no pivot point when it comes to forces, so you can't cancel out a force. Only in rotational equilibrium, if you put a pivot point at one of the forces, then the torque disappears. The force doesn't disappear, just the torque. So we can't cancel any of these out, but we wouldn't want to, because let's add up the numbers. 1298.5 plus the weight of the board is 98 newtons, and the weight of the man is 441 newtons. That's just 45 times 9.8. Let's just verify that. 45 times 9.8, 441. So let's just add up all these three numbers together. So 441 plus 98 plus 1298.5, and I get an amazing number here, 1837.5 newtons. And that's the total force up, so that has to be the total force down. And boy, oh boy, right down to the penny. Exact. Okay, excellent. Let's just take a break here, and we'll continue on with the next video. Remember, smash that like button, subscribe often, leave your comments and share this with all your friends. All your peeps want to know what this is. Anyways, see you next video. Bye-bye.